Okay, so here's the last lecture of AP Physics 1.
No.
Oh, it is. Okay, Monday review, take the final on Tuesday.
And then we
So,
move on to AP Physics 2.
Captain Sean, you don't have to look that happy about it.
What?
You don't have to look that happy about it.
I mean, I'll fade into the mist.
Okay?
Yeah, you'll fade in.
So, all of these equations are going to come from this purple sheet on the section where it says mechanics and fluids, and it's the bottom right-hand corner. Okay? So, none of them are particularly difficult, but yet they all kind of have their own little glitchy things to them. So, let's start with this equation where it has this equation for pressure. So, when you look at pressure, and particularly how it applies to a pen that I can't find. Where my pen go? There it is. Okay, so one thing you have to, the difference between like absolute pressure and what we call gauge pressure. So technically right now, we are under about 1 atmosphere of pressure, which is about 14.7 psi. So if you have like a pressure gauge that reads like absolute zero, when it's like it in a vacuum, it reads zero. When you take it out of that vacuum and put it in our atmosphere, then it's going to read 1 atmosphere, 14.7 psi, whatever it is, okay? Because if you establish a vacuum as being zero, we're more than that, which is a cool thing because we have an atmosphere. In reality, though, when you look at your, for example, your pressure gauge that you use to check your tires, okay? Right now that reads zero. So your gauge pressure basically starts at zero. In other words, we've already said we've taken our atmospheric pressure into account, and we're just going to let that be zero. So absolute pressure would start, you would start at zero and you would read 14.7. Gauge pressure says we've already taken that into account. We're going to start at zero and then we're just going to go up from there. So this is why when you look at these two pressures, one, this gauge pressure is just rho GH. So if you look at the units, and this is what we talked about, you've got density, which is kilograms per cubic meter. You've got meters per second squared, and then you've got meters, okay? Well, if you look at what's going to happen then, so you end up with kilograms meters per second squared, otherwise known as
Newtons.
well, and then per meter, which is newtons per meter squared, which is pressure. Okay? So, when you look at this one with this P naught, so this is the difference between the two equations. So P would be, you start at zero, you add in the atmospheric pressure. Gauge pressure already has that taken into account. So, if you look at this in terms of like water, so this is where this is going to play out. So what I'm going to do is that I've got a manifold. So I've got this big tube is connected to a bottom one that goes across like this. And then that water can flow up. So I've got the biggest one here. This is a little jiggly jag. This has like kind of a small reservoir here. And this one just goes straight up. So what I'm going to do is I'm going to fill this up to about right here. So I'm going to add water so that this one gets to about right here. So then what I want you to predict is what's going to happen to that height. So I'm going to go to this one right across here. So I'm going to stop it where this one is, if you drew a line, I'm going to stop it where this one is here. Okay? So what's going to happen to the heights of the other two? Are they all going to be the same height? Is one going to be higher? One going to be lower? Cohen.
That was mean.
Why? Because I said Cohen?
Yeah, because I'm thinking.
Not allowed.
I would say
That's kind of what I get paid to do, is make you think.
Right, pressure pushes down, so it's gonna want to put them in equal. They'll have the same amount of water in them, but like the one with the reservoir is gonna take more water,
Yeah.
so like its height will be lower.
Okay, so you're thinking, even though this is like this little jag in it, and these are much smaller, you're thinking this one, since it has the reservoir,
Will be shorter than the other two,
so it's gonna be maybe like down here?
but the big reservoir is gonna drain into those two, so it's gonna go down too, but only the amount of water it can drain, right?
Okay.
I don't know.
So here's my question. So I've got this setup, right? So I've got a straight one over here. I've got this one. And then I've got the jiggity jag. Okay,
Great art style.
alright? So I'm gonna fill this one up to here.
Mhm.
So Cohen's saying this one is going to be lower, maybe something like that,
Yes.
okay? So we'll call this A, we'll call this one A, B, C, and D. So if you were to rank the heights, Cohen,
Is this it?
how would
just
you
the
rank
heights
the
of
heights?
just the heights of BCD.
Huh?
Just the heights of BCD.
Oh, A,
All of
B,
them?
C, D.
Yeah. They're all.
Well, A's probably got the most.
So A is gonna be
volume.
greater than,
So A will be the shortest.
the shortest, like it will be down here,
Sure.
okay?
There's got to be a twist though, so maybe they are all equal.
That's what's probably gonna happen, but I don't know.
I'm gonna roll
So
with
my guess is A, then C, and then B
Hold
and D are
on.
gonna be
So
the same.
A is gonna be less than,
C,
okay?
and then B and D are gonna be the same.
And then
Be equal.
B and D are gonna be bigger than C,
Yeah.
so, but they're gonna be equal. Is that right?
Yeah.
So A is gonna be the lowest.
Well, no, it's probably not right, but
I'm
it
just
is what
saying,
I-
this is what you've got, we're gonna play the hand that you're dealt. This is what you're saying, right?
Yeah.
A is gonna be here, B is gonna be here, and then C and D are gonna be up here.
Yeah.
Or these two are gonna be up here, B and D.
Yes.
Okay.
Sure.
Yep, Sean?
Why you skip me?
Because he has the most contemplative look on his face.
No, well,
I hate how Bird just has a bunch of
think
inputs
G
to make
could
us
be the highest.
confused.
Do you think D could be the highest? Why?
It's the smallest volume.
Smallest volume, because this has to like jag around here. So since that's gonna be the simplest.
Oh yeah, if you were
what,
gonna straighten
what
that one
angles
out, it
are
would
the
be
what are the angles of the zig and the zag?
That's probably about 80 degrees, that's probably about 70 degrees, and that's about 90.
This is not a check identity. We have no way of knowing.
9 degree is what we want.
Yeah. So you're thinking
I didn't
D's
think
gonna
about
be the
that.
highest. Then what about the other two? What about the
Actually, yeah.
other
Wait, can you add just a little less? I forgot that if you on the idea that the volume matters, if you stretched out the Jag one, right, it
Yeah.
would be longer, so more volume. So can you add just a little,
What do you mean a little?
between B and D, that is less sign,
Yeah, I guess we're less than.
less.
So less than, greater than.
D is greater than B.
So less than.
Yeah.
B is
So
less
there?
than. Yes.
The alligator eats the bigger side.
Yes.
Okay. Are you good with that? Colin.
Well, I think the one on the left, the D, is going
Okay.
to be the highest
All right.
because
It's a straight shot.
yeah,
Okay.
and also volume, yeah, and then
Who had the camera going again?
Yeah.
Okay.
and then I think the
So you're gonna say D is gonna be the tallest.
yeah, and I think the two lowest. I think the A will be the lowest, and
So A is gonna be way out here on the end.
then B is going to be next to that.
So B is gonna be in here,
Yeah, with A being greater than B.
okay? A being greater than B,
Less than.
okay?
Eats B.
And so what do you thinking with C then? Gotta put C in there somewhere.
Greater than or equal to.
No, you can't be greater than or equal to. It's
don't
either
get a
equal
choice.
to, greater than, or less than.
I guess just do a straight like. Did I just do what Cohen did?
No.
No, okay.
You switched B and C around.
Okay. Yeah, I'm fine with that.
So
Or
what do you want in here? Less than or greater than?
Alligator eating. C.
That?
Yeah.
Okay. Well,
You're gonna pour the water into it and it's gonna fly away. I'm gonna
yeah,
do.
none of you are right. It's just gonna explode. Physics teacher killed while pouring fluid into a glass.
That's why you gotta use C.
That's what it feels like sometimes. I feel like you have like a ton of instruments designed with the sole purpose of making us wrong.
That's so rude.
But it's
I'm gonna
Well-
do something radical here.
What are you gonna do?
I think A is the highest, C will be the lowest.
So A is gonna be greater than, and C is gonna be out here
He's
on the
cooking. He's
end.
cooking.
Yep.
Okay?
And then we're gonna have D is less than A, and then B less than D.
So this sequence,
Yes.
Danny?
What?
I'm going to do D's the highest, then going to B, or, yeah, going to B, A, and then C.
So you're just gonna switch these two,
Yeah, that's it.
okay? Preston, this is a lot. What do you got?
I'm just gonna go everything equal.
He's gonna go out on the limb.
That's actually a good.
Interesting.
Decent
Yeah.
shot.
Going out on the limb saying they're all
That's-
wide.
All roads lead to Rome.
Say pressure. Sure, pressure.
What
Pressure.
about, okay, you gotta get a little bit more
The diversity of the answers.
explicit than just pressure.
Look how thick the wall is.
Well,
Perfect.
You add another one.
Yeah.
A has more pressure going down
Why?
because the volume is bigger, so it's got like
Oh,
more
I didn't
pressure per.
This was gonna like,
Okay, so if A has more pressure, shouldn't that push that down further?
it's gonna push more
Yeah.
water down.
Oh, but it's gotta push more water down as well, right? Because it's got more volume
Go and
inside,
Not your turn to speak.
right?
Hush.
Again, we got the finger wag.
Well, I mean, mother
The-
likes to be lazy, so I don't think.
Are we ready?
B-
Yes, so
I
let's
don't
see
think
it.
we'll ever.
I even have colored water.
to
Let's
show that
see
it's.
So make sure that the studio audience can see this.
Yes. Studio
one
audience.
second.
Okay, are we
This
ready?
is more exciting than the time
However, they are not live.
explosion.
Why does all be
Not the live studio audience.
What do you know? They're all equal.
How interesting. Preston was right.
Huh.
Because the change in pressure is proportional to the change in volume that it has
How did
to,
you
of
think
water that has to move. That
D-
makes sense.
C is slightly lower if we just look at it really closely.
The
No.
cer-
Okay, now here's an interesting question. If you were to measure the pressure across the bottom of all three, or of all four, if you could put like a tiny little pressure gauge here, 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 and here, which one would have the highest pressure?
A, D, the one on the big one.
This one would have the highest
Yeah.
pressure. Why?
There's the most volume above it.
Okay? Now, let's look at this equation right here. That the pressure that you're gonna feel is P naught, all right? So if you were to put a pressure gauge down here, so P naught would be your atmospheric pressure, okay? 101,300 per square meter. Rho would be the density of the water. G and then H would be the height of the column.
Pressure has nothing
Where
to do
does
with
area
volume.
fit into that equation?
No.
It doesn't. They would all have the same area. Excuse me, they would all have the same pressure because area is not a factor. So if you could put tiny little pressure gauges in there, they would all read the exact same thing.
Huh.
Huh.
What do you know? Because volume is not a factor
Physics is
in the
dumb.
equation.
Physics
Okay?
is
Or
stupid.
we're gonna make it even dumber,
No.
okay?
That makes me feel dumb.
Dumber and
So
dumber.
now I've got, this is the original U-tube, okay? Literally, this is a U-tube, okay?
The YouTube.
So I want to pour some water in here. Okay? And oddly enough, it goes to the same height. True?
Yep.
So the pressure here is the same, pressure here is the same, pressure. Now, as you, for those of you that swim, okay, if you were to swim down to the depths of this, what would happen to your pressure?
We go up.
It would go up, because if you look at this equation, and this is P equals P naught plus rho GH, okay, or depth. So, again, cross-sectional area, not part of the story. So the deeper that you go, and this is if you ever go on a submarine, you need to know this, but the deeper that you go, what happens to the pressure on top of you?
It
It increases, because now you have more and more stuff above you pushing down. Cool. Now, we're gonna change it up a little bit. So I'm gonna take this, and then I'm gonna pour oil onto one side, okay? So, here was the U-tube. We got water here, we got water here, okay? Right?
Good job, Chloe.
Good stuff.
Try
You're
put
trying to
up
move
and
it
then
back
use
to
the
the
The camera is just so
I know.
special.
Maybe Santa Claus can bring me a new camera.
No, just the tripod.
Okay,
The mini.
So,
the mini. D
I'm gonna
tripod.
pour oil onto,
Held together with
this
tape
side.
and souls of
so I'm gonna have
physics
some
students.
oil, when you look at it, I'm gonna have the oil well, according to that diagram, I'm gonna put it on this side, okay? I'm gonna have oil over here. So when I add oil to it, first off, what's more dense, water or oil?
Water.
Water. Oil floats on top, okay? So when I add the oil to this, what's going to happen to the amount of the level of the water?
Nothing.
Nothing. I'm gonna add oil here and this is not going to change.
Oh.
I think the right side will
Will
increase a
increase.
little bit because then when you add more stuff on top on the left side, it'll increase the pressure
I
on
think.
the left side. So it'll equal out and
I think the
that'll
two will
push it up
explode.
slightly.
I think it'll.
So here's the question. Here's the question. I'm gonna add some oil here and that's gonna create some downward pressure, right?
Yeah. In proportion with
So this is going to go up, true?
Yes.
So here's the question, are they still going to end up at the same height?
No.
No,
No.
because the oil is less
Less
dense
dense.
than the water.
So which one's gonna be higher, the oil side or the water side?
The oil
oil
side.
Oil side.
Why?
Because it can only push down on the water with the amount of whatever
Oil.
gravity and mass it has, but because it's less dense, it doesn't have. It can't force as much water out of the way.
Okay, all right.
I still think
So,
it's gonna be-
actually, we'll come up there and deliver the help.
Berg prepares to blow our mind. He pours in the oil and it just like gravitates to the other side.
Yeah.
Hey,
The oil actually flows
Camera.
over to this side.
camera, going.
Oh, Chimera.
Chimera.
Kamala.
Okay, are we ready?
Oh, I didn't account for being on that side. He does nothing.
What? Berg, stop cheating.
I'm not cheating.
You are cheating.
What kind of oil is that?
This is slight difference.
Hyper dense
Pure
water oil.
He's hacking.
This is slight difference. It's not
Okay.
like
Water.
I don't think.
This
Berg
makes
is hacking.
no. What?
Okay,
Berg is hacking.
so you're right,
Okay, we're good.
right? So the oil side is
A little bit higher than the water side.
from the water side, okay? And notice that they don't mix, right? Because one of the things, this is the chemistry side of this, is that likes dissolve likes. So the oil doesn't like the water. So at that interface, they don't like each other. So here's the question though. If you were to put a little pressure gauge right here and a little pressure gauge right over here, okay? Would the reading be the same?
No. Wait, yes.
Yes.
Yes. Sorry, I had to think about that one for a second. Because that oil
Displays
has the
that.
same amount of mass.
Oh.
Well, no, sorry. That oil, the
Less dense.
because it's less dense, can only displace the same amount of water.
Don't,
this side, right?
lose the displaced thing.
Or not displace, but like move.
Okay,
Push.
let's look at
Pressurize.
this. Let me kind of draw this again, okay? You have the right idea, Cohen, we just need to work on some terminology.
Yeah, I'm not
Okay.
sure how to like vocalize.
So we had oil here, and water was a little bit less. So when I go across these 2 points, the pressure is
the same.
the same,
Yes.
okay? Pressure is the same. So if you look at rho GH, P naught plus rho GH, is P naught the same for both of them? Because that's your atmospheric pressure.
Yes.
That's the same for both of them. So if I want the same pressure down here, if you look at rho GH, oil is less dense.
So it has
But
a
your
greater
H
height
will be
accordingly.
bigger.
But my H will be bigger to create the same
Over there.
over there. Okay? Does that make sense?
Yes.
Okay. All right. Cool. You got that one.
we got one. We got one right. Yay.
Going. Yay. Yay for going. Okay. Now, so that's that. So here's what I want you to see out of this. Is that,
My third.
number one, these all have to be the same units. So rho GH gives you the same units of pressure as newtons per square meter. If you're talking about gauge pressure, don't worry about P naught, we've already taken that into account. So, the next one I want to talk about is this area 1, volume 1 equals area 2, or velocity. So, on this one, let me write this over here.
Not volume. He's meant to say velocity.
A1, V1 equals A2, V2. So this is going to be your cross-sectional area in meters. This is going to be a velocity in meters per second squared, meters per second. So what units do you get out of this?
These are the same.
Meters cubed per second.
Meters cubed per second. Meters cubed is a measure of
Volume.
volume. So here's what this means. This is a flow rate, okay? This is the amount of volume moving through a system per unit of time, okay? So instead of velocity being like meters per second, which is how far you travel per unit of time, this is what volume moves through it per unit of time, okay? Now, so what I'm going to do is I'm going to take yonder syringe and I'm going to pour some water into this, okay? So I got this. So, when I push this out, when I push this, what's gonna happen on this end?
It's going to eject the liquid.
Fluid's gonna come out. So here's the assumption that you make on a problem like this, is that when I push this plunger through, we assume that the water cannot be compressed, okay? It's like a slug. So whatever volume of water is moving here per unit of time has to be the same volume of water that's coming out here per unit of time, okay? So I can't lose mass. Same volume has to be moving here per unit of time as here per unit of time. But in this section here, I've got a really, really big cross-sectional area. So this is gonna move slowly. So what's gonna happen over here to compensate for it when you have a really, really small cross-sectional area?
It's gotta move quickly. A lot
It's gotta move faster. So if you've ever held your thumb over the end of a garden hose, what happens?
It
goes
faster.
Faster.
Sprays
So if you look at this mathematically, so when I've got my syringe and that plunger back here, so this has a big area that's moving slowly, and that has to equal a smaller area that's moving faster, okay? Because there's an equality sign there. So this is why when I hold this up like this and I push this slowly, notice that water goes flying out like I can shoot this thing all the way across the room. So I can even hit all the way onto those cabinets. So I can make this move slowly and make that water come out fast. So it's a simple idea, but it's the same cross-sectional area. So as your cross-sectional area becomes smaller, your velocity has to go faster. Okay, so there's that one. So now we're going to tie this all together into this one big equation. Let me just start. I need to start all over with this. So this is what's known as the continuity equation, which is the longest equation that exists on the entire equation sheet.
Ew. P half PV squared equals P2 PY 2 plus half PV 2.
No, they're slightly different. I just panicked for a second because I was like, they look pretty similar, but this one
Okay.
is slightly less steep.
So this is what's known as Bernoulli's continuity equation. So let's kind of talk about this in terms of units. So obviously this is going to be pressure, which is going to be in what?
Newtons per meter squared.
Newtons per square meter. Now, this is going to be rho gy, right? So that's also going to be in, that's what we just proved, that's newtons per square meter. Now, this one here gets a little bit wonky because it's 1/2 density times velocity squared. So you've got density in kilograms per cubic meter, and then you're going to multiply that by meters squared over second squared, right? That's kilograms. So you can write that as kilograms meters over second squared, and then that's going to cancel out one of those, and you get per meter, so you end up with the exact same thing. So it's a little bit weird unless you think about it. So basically, this is the pressure side. Rho GH, if you think about it, is kind of like a potential energy side, which is like MGH. Okay, so this is like how high the fluid gets pushed. And then you have 1/2 rho V squared. So this is like a kinetic energy portion of it. So basically you have a pressure, a potential energy side, and a kinetic energy side of this, okay? So here's the idea. So let's say that your pressure is the same on both sides. Let's just say that's the same. So here's what I want you to see, is that if everything has to be equal, if one has like a higher velocity, then that has to compensate by the other part being lower. So here's what we're going to do. I'm going to take this, I didn't take this out, I didn't get rid of this. Hold on, give me a second. Okay. So I'll take yonder ping pong ball, put it in there, oddly enough I let go of it, and what happens?
Falls out.
Falls. So how can I make that ping pong ball, holding it like this, how can I make that ping pong ball stay in there?
Pressure.
Pressure, by doing what? Okay, so I can suck on it. Cool, right? Goes like we thought. If I blow on it, what's gonna happen?
It shoots out.
Shoots out, okay?
Huh?
Oh,
Ah.
wait, what?
Ah,
Direction doesn't matter.
ah.
Oh, it's a scalar, not a vector quantity? Scalar, not vector.
No.
If you do it hard enough, I think it will.
As a matter of fact, if I don't blow fast enough, it falls out. But if I blow faster,
It's got to do with something.
stays.
with the air moving
Is it
around
like a
the
system
ball.
with like lift? Where
what'd you
it
say,
goes-
Danny?
A system like lift.
Kinda.
Oh,
So, like,
is the
Oh, Will,
Is the-
Will has a breakthrough moment.
is the air like moving around the ball and then creating a higher pressure underneath it, keeping it up?
Or
Close.
lower pressure on the other side.
So here's the story. So the faster it goes,
The faster it spins.
The faster the air leaves the system.
well, let's
So
talk about pressure,
the-
right? So clearly, when I do this, because if I just let go of it, it falls, right? But if I blow fast enough, it stays there. So is gravity still pulling it down?
Yes.
Yes.
So there has to be something balancing out the force of gravity to make it stay there, right?
Yep.
Okay? So here's the idea. If you look at this continuity equation, if you have one side getting bigger in terms of velocity, to balance it out, the pressure side has to get bigger. Okay? So here's the basic idea. The faster the air moves, the lower the pressure. So Danny mentioned the concept of lift. So if you look at the design of an airplane now, right? As a curved surface over the top. So as the air moves across there, that air gets split. Goes like this. Okay? So that air is going to meet back over here on the opposite side. And it's going to meet at the same time. But the air going over the top has to travel faster. So since that air has to travel faster, what do you know about the pressure on the top of the wing?
Less.
It's less. So the air, because that's moving faster, that creates a low pressure on the top of the wing. As that creates a low pressure on the top of the wing, just like Danny said, what are you going to create?
Lift.
You're going to create lift. Okay? That's what's going to happen. So, let me ask you this. I'm going to take a couple of pieces of paper, like this, and I'm going to blow air down between the two of them. Okay? So I'm going to do this. I'm going to hold them like this. I'm going to blow down between the two pieces of paper. Three things could happen. They go flying apart because I'm gonna blow air down between them and it's gonna force them apart. Two, there's still pressure and it's still in an atmosphere and everything's gonna equalize and they're just gonna, nothing's gonna change. Or they're going to get pushed together.
Probably pushed together.
Push together because it seems counterintuitive, and that's what all of today's been about.
That seems so rude.
But am I wrong?
I think of the two pieces of paper as two wings.
So
flying.
this one's going faster. So this one has
It's
less
faster.
pressure.
It creates a low
Yeah,
pressure.
Way
Environment,
Goes-
so it
yeah,
steps in.
through here.
Faster here, so slower out here, so lower pressure here. Hold together.
Okay,
That's-
you ready?
One point for counterintuitivity,
counterintuitivity,
or whatever it is.
Now, here's one way you can look at this.
Do that with the oil now.
So here's your two sheets of paper. If everything's static, what do you know about the pressure on both sides of the paper?
They're the same.
They're the same, okay? Because you have collisions with the atmospheric particles on both sides, and you have the same number of collisions on both sides, right? Now, when I blow through there, I'm forcing that air down like this. So what's going to happen to the number of collisions with the sides of the paper on the inside?
Less.
It's going to become less. But I'm still going to have the same number of collisions on the
Outside.
outside. So therefore, it gets pushed together because of an imbalance of force. So same thing is true if you look, this is a top-down view of like two cars racing like in NASCAR. Okay? So this is the top-down view. So what happens to that air in between the two cars?
Low
It's
pressure.
moving faster, so they get pulled
Goes
towards
faster.
each other.
So they basically get
Pulled close to each
pulled
other.
closer together.
They're like two pieces of paper.
They are. They're like two pieces of paper. Okay.
And they smash into each other. and
Now, let's
explode.
talk water fountains. Okay? So, here's your ground level. Here's your water supply pipe. And it's going to come up to a water fountain like this.
Just a
Okay?
hose out of
Which
the
looks like the
ground.
Loch Ness Monster. But you get the idea. So, we're going to
Opening
look
mouth,
at
it's like a very unmuscular dude trying to.
P1 plus
It's over there.
rho GY1 plus 1/2 rho
Looks kinda like a
V1
horse.
squared.
Like a horse.
It's over there.
It's a who?
It's Loch Ness Monster. It's Nessie.
From a physics standpoint, is it real?
Oh God, no. Absolutely not. And geologically is the biggest thing. So everybody says, oh, it's an ancient dinosaur. Well, if you look at when Loch Ness formed, it was well after the dinosaurs would have gone
What
extinct.
if it was a modern dinosaur?
Like a chicken?
Okay,
Yes,
you know,
the
just,
bird.
just stop. Okay.
Or a gator?
So, what do you know about the opening of a hydrant or like a faucet or a drinking fountain? Is it small or is it big?
It makes
Small,
Small.
comparatively.
Okay. So what that means is that this is going to be 1/2 rho G1. So, because of the fact that, and this is where you have to combine the ideas of A1 V1 equal A2 V2. So, do you think the water supplies, the pipe that supplies the water, do you think that's a big or a small diameter?
big.
Big, okay?
Like a lead.
So this is going to be like a big pipe that's going to supply the water, okay? And then you're going to have a small cross-sectional area up here. So if you look at A1 V1 equals A2 V2, right? So this, we're going to call this the V2 side of this. So over here, what do you know about the cross-sectional area of coming out of that drinking fountain?
Very small.
It's very small. So it's gotta be, but it's gonna be moving
Faster velocity.
faster, right? So down here in the supply line side, you've got a big area, but it's going to be moving slower. So this is going to be V1. So here's what I want you to see. This side here, this part of this equation, that's going to be 1/2 rho, and then you're going to have a small V1 squared. And then over here, this is going to be 1/2 rho, and then you're going to have a bigger velocity squared. Okay? So we got that idea. Okay? Low velocity water underneath the ground, high velocity water coming out. Okay? Good with that idea. You got this visual. Oh, what's that?
This is your drinking. This is my imitation of
Handle
drinking
this
fountain.
one.
Oh, or the swan. Okay.
Yeah.
Now, if you're clever, and you are, what are you going to let y1 is going to be your depth? If you're clever, what are you going to let y1 equal?
0.
0. We're going to let that equal 0. So that means that this, like let's say it might be like 2 meters below the ground, 1.5. This is going to be some depth. So here's the point. This is not going to be 0. Okay? So here's what I want you to see. There's an equality sign in between.
What?
So that means you've got the rho g y2 part and the 1/2 rho v2 squared. Those are going to be big numbers. But this part of this equation here is going to be 0. So how are you going to compensate for that?
Big.
Something's got to be big.
How about
Pressure.
the pressure?
Sure. Pressure.
Right?
It's got to be huge.
Pressure 1, right? But then what's going to be the pressure coming out on that side?
Smaller.
It's gonna be less.
That's going to be smaller. So basically how your water distribution system works is that you have a big supply line under high pressure with water that's moving slow. Then on the other side of that, you have a low pressure coming out, and then you have, because now you have a height, you have a potential energy part of it, and it's going to be moving faster. Okay, Cohen, give that a spin. So over here to
I'm in Spain without the S.
Where are we going?
right here. Okay, so let's talk about this. So we said that area 1, velocity 1 equals area 2, velocity 2.
Yeah.
So I'm going to turn this on,
Yeah.
okay?
Mm-hmm.
As the water falls, what's going to happen to its velocity?
Increase. Accelerated gravity.
It's going to increase. So what should happen, since it's going to fall faster, what should happen to its cross-sectional area?
It will
Increase.
decrease.
Decrease.
Wait, cross section.
Right?
Oh yeah, yeah.
Right? So if you look at what happens, when that water comes out, you start with the bigger cross-sectional area up here, and then as it falls, that narrows.
Smaller.
Because you have the same volume of water moving up here as you do
Down there.
down there. So as that water falls, it actually tapers because the velocity is getting bigger, and to compensate for that, the cross-sectional area has to get smaller. Okay, so this is like the classic example. So supplying this water underneath the school, there's a big supply line. So this is coming out fast with a small cross-sectional area, but it's got a low pressure. So underneath the line, you've got high pressure moving
Slowly.
slowly. There you
Cool.
go. That's it. All right.
Sink did the sink the cheapest demo you do.
I turned on
Okay.
the second.
So
I could probably do that one at home.
okay. So here's what I always do on this last assignment. Okay?
Uh-oh.
I'm going to write down the questions, the problems, questions that you need to do. I suggest that you look at them. This is not due in the sense that you're not going to hand it in. On Monday, I'm going to give you a copy of this answer key. Okay? I will run this off. You will have this. So you're not going to hand it in. If you want it, if you read the problems and go, hey, I got this, then don't worry about it. Okay? But if you read them and you go, oh, this is bad, okay, that might be something that you consider. But like I said, I will give you copies of this on Monday.
Cool.
All right.
Thanks, Bird.
You're welcome.
My hero.
Krishan needed that for his grade.
Oh, are you done with my?
Mr. McKippin, we handed in, can you get a perfect score?
Oh,
Please. Honestly, I feel like we've earned the points.
I think I want more points in my grade book right now.
Where are you at?
I'm around 92.
Okay, you're fine, buddy.
It's not gonna.
It's to
Oh,
the
yeah,
point
you're
now, because like,
I want no more grades in
I will know, like, when I input a score, like, if it's kid's score changes, like, if it changes color on one side of the screen. And this is the point now, we have so many points on labs and homework, and some kids, like, literally, like, their scores are so consistent. And this goes out to, like, the nearest hundredth. Like, I will input a score, and their score does not change.
Dang.
Like, and they're that consistent, like, literally, like, it doesn't even change 1/100th of a percentage point.
That's me, but like in the wrong letter.
I'm not casting stones, okay?
Nice. I've been
I wasn't really consistent at the start of the year, so.
It's kind of been a roller coaster.
I still don't understand how Graham did better.
My semester
this
started
Yeah, I
with
did.
a very
than the first
big,
term. That makes no sense at all.
a very big
But-
drop.
It's true.
Maybe you just locked in.
He said it was
Oh.
easier.
Wait, that reminds me. I need to look. Maybe he has put it in because we all took it. Calc test
Oh my
was a
gosh.
thing that happened.
Opening your Chromebook to Reddit is kind of
Shh.
What are we doing?
I was checking r/Soaksong to see if it was in
Okay,
the
kids,
I'm glad we got that on camera.
No.
they're all out of the book.